Hi guys, welcome to another session of Bootcamp 2020. And today we are going to have a look at the AWS Neptune, which is a graph database. So Sir Zia may join us soon. He was having some internet problems. Um, okay, so up till now we have seen quite a few databases in AWS. So initially we saw DynamoDB, which was a NoSQL document-based database. And then we saw Aurora serverless in the last class that Homa taught, and we saw in Aurora serverless, which is a SQL database, that we can maintain relationships between items in different tables. Now the problem is that when the number of relations increase or they become really complex, then the SQL database cannot handle them. It becomes really hard for a SQL database to handle them, and most importantly, it's really difficult to query these complex relationships using SQL. And this is where graph database comes in, that we're going to study today. So the AWS service that allows us to create and use graph database is called Neptune. And a graph database basically creates relations between entities or items inside it, just like SQL, but in a very different way. So instead of creating tables, it creates graphs, like an entire graph, it looks like a spider web that has a lot of different vertices and edges. So these vertices and edges are basically building blocks of a graph, and we'll have a closer look at the edges and vertices in few minutes. So you would basically use graph databases in applications like social media, like Facebook. So in Facebook, like, it's really easy for me to find friends of my friends that went to my school. So although it's a very complex query, but it's very easy to run in a graph database. And not only that, but in a website like Facebook, a social media website can have thousands of different relationships. Like, even a user in Facebook can have thousands of different relationships. Like, a user is related to comments that he makes, pictures he's tagged in. He's related to his friends of friends, the people who he's chatting with, the chats. Um, yeah, and the groups, the pages, and then the list goes on. So there can literally be thousands of relationships for each user in a graph database. So today we are going to look at AWS Neptune. So let me share my screen and I'll go through some slides. Hmm. Oh, sorry. So Homa, can you see my screen? Homa?
Yes, I can. Yes, I can see now.
Oh,
It's visible.
okay. So basically, AWS Neptune supports two different kinds of graphs. One is property graphs and one is RDF graphs. We are only going to look at the property graphs. So these are different types of graphs that can be made inside a graph database. And the basic elements, vertices, and edges that I was talking about property graphs. So we are only going to look at the property graphs. And the query language that is used with the property graphs, that is commonly used with the property graphs, is called Gremlin. So we are going to look at how to make property graphs, and we're going to look at Gremlin. We may not discuss Gremlin in too much detail in this lecture, but I'll show you guys a few queries. I'll run a few queries for you guys. So this is the next slide. So I told you before that the graphs are made using vertices and edges. These are the only two basic elements of graphs. Only vertices and edges create a whole graph. It can be huge graphs. It can be huge graph with many vertices and edges. Now we need to understand that what is an edge. Sorry, what is a vertex and what is an edge, and when do we need to create them? So a vertex is usually made for entities. You can see over here it's written. Vertices are usually made for domain entities. And what do I mean by entities? Basically nouns. A user is an entity. a book can be an entity, a restaurant can be an entity, uh, I don't know, a tree can be an entity. Basically, mostly you can say the nouns like a user, a book, things like these. Now, a vertex can have labels. And what does label tell us? That what kind of entity is it? The vertex that I'm making, what kind of entity is it? Is it a person? Is it a product? So you can see they've given two examples: a person, product. It can be a book. It can be a restaurant. In a social media application, it can be a user. So label actually tells us that what is the type of this vertex. Like, is it a person? What am I creating in my database? Am I creating a person? Am I saving the information for a person or a book or a restaurant? Just excuse me. I think Sarzia joined in. Yeah. Sir, would you like to add anything? I'm in the middle of the lecture.
Go ahead. Go ahead.
Okay. So saying in the label you actually write the type of the define the type of the entity. So it can be a person, like basically what kind of data you're trying to add into the database. So it can be a person, it can be a book, it can be a restaurant, it can be a tree, it can be a user. Like it can be a person, it can be a book, it can be a restaurant. So this is what you what and what goes in the property is the attributes related to that entity. Like for example, if my label is a person, then in the properties I would add like the name of the person, the age of the person, the address of the person, the email address of the person, things like these. So if my label is a book, it's common sense to write properties of a book. The properties of the book would be the author, the number of pages, the title of the book. So if my label is a restaurant, then the properties would be the name of the restaurant, the location, things like these. So uh, this is how you create vertices. Now let me revise this. You create a vertex for an entity whenever you want to create an entity, and in a vertex you can have a label that defines what kind of entity is it, and then the attributes related to that entity go into the properties. And then you have the second type of basic structure, that is edges. Now edges are basically used to define relationships between two vertices or two entities. So here we were making entities, and edges are used to define relationships between two vertices or entities. And just like vertices, we also have label and properties in the edges. So in the label, you would mostly write the kind of relationship that that exists between those two vertices. And in the properties, you can write some more metadata for that relationship. Let me show you an example. So this is a very simple example. You can say that it's a snapshot of a graph database that was taken from a social media website. So the green circles over here are vertices. We have three green circles over here. So you can see we have three vertices in this snapshot. And the label, I told you there's a label and property for properties for vertices. So the label of the vertices is mentioned in this white rectangle. So the label for all three vertices is same. And what do we mean by label? The type of entity that I'm trying to make. So I'm trying to create three users over here. Now, because each one of these vertex is a user, the label is same. It's all three of them are users. But we also have some properties. So you can see, so the property comes in key value pairs. So the key of all the properties is same. So we are saying that we actually want to save the first name and last name of all the users. But obviously the value would be different. Like the first user, the first name of the first user is Ellis and the last name is Jones. For this, the first name is Bob and the last name is Smith. For this, it's Dan and Wilkins. So we have three users. This is how you read it. We have three users in our database, and all of them have a first name and a last name, but their first name and last names are different. So this is how you define vertices. Now you can also see some lines uh, in between these vertices, and you can actually um, see that these are directional lines. They're like arrows. They're going from one vertex to another. They're pointing towards another vertex. So these are called edges, and they are directional. Be mindful of that. And again, just like vertex, I told you that edges can also have a label and some properties. So the label of the edges over here is this follows. And the label for both the edges is same, follows. So the way we will read this is that is the user with first name Bob follows another user with first name Alice. So this edge is actually showing us the relationship between the two vertices. We're saying that this user is actually following this other user. So we have created a relationship between two vertices, and the same goes over here. So here you can actually read it like Bob follows Dan, and but you can see other than the label, we also have a property in the edge that is since. So here we are saving the date at which Bob started following Alice. So we can read it like Bob follows Alice since 2019 1010, and Bob follows Dan since 2020. So we have saved some metadata with the relationship that when did he started following the other user, and the label tells us the type of the relationship that two vertices have with each other. So this is how you basically create your graphs. It's quite easy, but there are some techniques that you have to use to make to actually make your graph handle queries more efficiently. We might not discuss them today. We might discuss them tomorrow. But this is how you basically create a graph. So now let's get back to the Neptune. So the problem with Neptune is that it needs to be created within a VPC inside a subnet, and VPC is not easy to understand. Uh, Although we have like discussed VPC quite a few times in these sessions, but I think we have not done justice to it. So I'm quickly going to go through VPC. Although it's a very big topic, but I'm going to try and skim through it. The second thing you need to understand is that Neptune is a cluster database, so it can have more than one instance. It creates more than one instances. And why do we need that? Let's see that in the next 2 points. So these 2 points were taken from the documentation of Neptune. So it's saying that we have one primary database instance. So when you create a Neptune database, you have one primary database instance. And what does it do? It supports read and write operations and performs all of the data modifications to the cluster volume. So it's saying that the primary instance can do read and write operations in your database. Each Neptune database cluster has only one primary database that is responsible for writing graph database contents. So it's saying that you can only have one primary database instance, and this primary can also do write operations. Now there is another type of instance as well that is called Neptune replica. So what does it do? It connects to the same storage volume as the primary database. This means that it can access to the same data that was accessible through the primary database instance, like it can access the same graph, and supports only read operations. Now this is important to understand. Your primary instance can do read and write both, but there can only be one primary database instance. Your Neptune replica can only do read operations, but each Neptune database cluster can have up to 15 Neptune replicas in addition to the primary database instance. But you can have 15 different Neptune replicas. Now, why do we need 15 different Neptune replicas? Why do we need 15 different read instances? It's written in the next line that this provides high availability by locating Neptune replicas in separate availability zones and distribution load from reading clients. So this just increases our availability. Like you can have different instances placed in different availability zones, and if one availability zone goes down, or if one instance goes down, the other one can take over. Or you can also distribute loads to different replicas to reduce load on just one instance. So the basic idea behind having many different instances or Neptune replicas is to increase the availability. But by default, when you create your Neptune, you just have one primary database and one Neptune replica, and then you can create as many as you want, up to 15. Now, as I told you that Neptune needs to be created within a VPC, so I think we should discuss VPC. Although it's a huge topic, I'll try to keep it short. I'll just try to go through the important things, and there might be a few things that you guys might not understand. So just bear with me. So this is the so let's first go through the VPC. So this is the this is the definition that I found in the documentation of AWS. So VPC is a service that lets you launch AWS resources in a logically isolated virtual network that you define. Virtual network. So basically, you can have your own private network, which is not connected to the internet by default. And why would you need a separate networks? Just to increase your security. Like you can have your own network, and then you can define your own security rules that who can access your resources in that network. So if you want to have some resources that you don't want people from internet to access them, you can actually put them in your own virtual private network, and then you can define some security rules on it or some firewall on it that only requests from certain IP addresses can access these resources. This virtual network closely resembles the traditional network that you would operate in your own data center, with benefits of using scalable infrastructure of AWS. So it's just saying that AWS takes care of everything, the maintenance and the scalability issues for you. So your Neptune actually works inside a VPC. So that's why you need to learn about VPC first. Now, I would actually like to go to the VPC console and show you a few things that you can do. So you can see it's a huge. It can be a huge topic. You can see the amount of stuff that we have over here. But I'll just show you the important stuff. So let's first create a VPC that you would need to create a Neptune cluster. So one VPC would always be there in your account by it is created by default by Amazon, and try to never delete it. So I'm going to create a VPC. So this is the name, test VPC. Okay. So this is very important to understand that what is IP4 CIDR block of your network. Now this is not easy to explain because it requires a lot of maths, but I'm just going to try and explain you the concept behind it. So basically you are by creating a VPC, you're creating your own network. So whenever you create a network, it has a network ID or a network address that looks something like this: some number and slash some number. Now every network can, so assume that this is my network, and now every network can obviously would have some devices connected to it. Now let's say I have 3 devices connected to my network. Now each device in a network has an IP address that identifies that device in a network. Like if a request comes from a particular device, it is recognized by its IP address. So you can see I have 3 devices inside my network. The first device has this IP address, which is going to be unique in the network. The second device has this IP address, and the third one has this IP address. So you can see all these 3 devices have different IP addresses, but let me just write over here. But the thing that is changing inside the IP address is just the last segment. So you can see you have 4 segments inside your IP address. Only the last segment is changing with the IP address. And why is that? Because the first 3 segments, you don't call them segments, you call them octaves, but I'm just calling them segments because octaves is a technical term. Uh, the first 3 segments don't change because they are reserved for the identification of the network. So first 3 segments actually identify the network. So the first three segments in this IP address actually tells that this device belongs to this network. They are reserved for the network identity. Only the last segment changes with the device. So you can see 0, 1, 2. And this last segment is usually called the host name. So this segment is reserved for the devices in the network. So this is going to be unique for each device in the network. Now the problem is that now whatever I'm saying is oversimplified. It might not actually be true. I'm just trying to simplify things because this in itself is a huge topic. Now the question is that how many devices can you connect to a network? There has to be a limit, right? You cannot just keep going on. Now the number of devices that you can connect in your network is determined by this number over here that is written with this slash, and this is called subnet mask. And now I'm not going to go into details that how does it determine, because we have to do the maths in binary, and I'm pretty sure not everyone is an engineer over here. So let me just give you a formula that how can you figure out from this number over here that how many IP addresses, or in other words, how many devices can be connected to your network. So the formula is, so only Where's my mouse? So only this number can determine how many IP addresses or how many devices can you have in your network. So the formula is 32 minus this number. It is 24 right now. So 24, that is going to be 8. And then 2 to this 2 to this result, 2 to the power of this result. So 2 to the power of 8. So this will actually give you the number of IP addresses or devices that you can have in your network. So if I have my subnet, if my subnet mask is 24, then I cannot have more than 256 devices over here. So my IP addresses would look something like, it would start from 0 and it will go up till 255 because 0 is also included. So in total, so it would be like 10.0.0.00, then 1, then 2, then it will go up to 255 because I cannot have more than 256 devices in my network. So this is the role of this subnet mask. So the formula is 2 to the power bracket 32 minus this number. Now, and how do we decide these numbers? I'm not going to go into that. So let's just write down 0.0.0.0/24. Now this is interesting. Like if I wanted to connect like 300 devices with my network, then I would have had, wait, let me, yeah. So then I would have had to decrease this number over here. Now let's see if I make it 23, what happens? So 32 minus 23 should be 9. And what is 2 to the power 9? 2. So you can see now I can have 512 devices in my network. So if you want to increase the number of devices in your network, you need to reduce this number. But in AWS, in Neptune, in VPC, the lower range is 16, I think. So you cannot go below than that. So for now, 24 is okay for now. And then there's one more setting over here, tenancy. So if you leave it to default, though if you choose dedicated, then the AWS would actually use a dedicated hardware for your VPC, and that can be very expensive. So if you're just trying to learn things, then just leave it to default and create VPC. Now we have created our VPC and in other words, our network, and our network have 250 can have 256 different IP addresses. Now the next thing, subnets. Now to initialize Neptune, you also need to have a subnet inside your VPC. Now what is a subnet? Now whenever you want to divide your network into further segments, like if I have 256 different IP addresses and I want to divide my network into 2 different segments, each having 128 IP addresses, I can do that using subnets. So let's create a subnet now. So it's asking for which VPC you want to create the subnet. And then in the name of subnet, so I'm going to write public subnet. You can, again, just like Neptune, I told you Neptune, you can place your instance in different availability zones. You can also, it's a good idea to actually replicate your subnets in different availability zones, because if one zone goes down, the subnet in the other zone can take over. For now, I'm just going to put it in one zone. Now, when you're creating subnet, it's again asking you for the CIDR block. So for now, I'm just going to put the same thing, but I'm going to write 25 over here. And why is that? Now, previously I wrote 24. Why did I write 25 here? Let's do the calculation. So 32 minus 25 is 7, and 2 to the power of 7 is 128. The reason I wrote 125 here, because I only want 128 out of those 256 IP addresses that are available in my VPC to be present inside the subnet, and the other 128 IP addresses, I would put them in another subnet that I would create soon. So I want to create 2 subnets. In one subnet, I'm putting 128, and in the other one, I will put the other 128. So basically, I've divided 256 IP addresses into 2 different segments. So that's why I wrote 25 over here. If I had written 24, then all the IP addresses would have gone into this subnet, and I would not have been able to create another subnet because I wouldn't have any IP addresses left. And this is how you create your subnet. Now let's create another subnet. I'm going to name this private subnet. Availability zone. Now you can see I wrote 128 over here. Why? Because my first subnet took all the IP addresses from 0 to 128. And this second IP address would have IP addresses from 128 to 255. That's why I wrote 128 over here. So if I write 126 over here, it would give me an error. It would say that this IP address has already been occupied. Let me try doing it. So you can see overlaps with the existing subnet. It would only work if I write 128. Because 120 up till 128 have been taken by the previous subnet. They are not available anymore. So now we have created two subnets. Each of them have 128 IP addresses available. Now the next thing, this is how you create subnets. The next important thing that you need to understand is how to create route tables. Now every subnet that you create by default has a route table or a route table. And what does route table do? Route table basically, I'm just going to create a new one. Public route table. Which previously. So what does the route table do? It actually tells that how is the traffic redirecting from your network. So where did my, yeah, here it go. So you can see it has a list of routes that actually tells that how is the traffic redirecting or directing from your network. So right now it's saying that this is the IP address of my local network that I just created. So it's saying that right now it is only able to communicate within locally. It does not have internet access right now because I do not have any route that is going to the internet. Now, what I want to do is, first of all, I have created a new route table, and this first route is going to be there always by default in any route table. So first thing I can do is I can associate this route table with my public subnet that I just created. Now, the reason I'm calling it a public subnet is because I want this subnet to have access to the internet. So, okay. Now, right now it doesn't have access to the internet because we do not have any route or route going to the internet. Now, to give access of internet to your subnets, you need to create an internet gateway that is over here. This is the third important thing that you need to know. So create an internet gateway. You can name it anything. My gateway, and that's it. It's very easy to create. And what does internet gateway do? It actually allows your subnet to communicate with the internet. Now I've created two subnets. I've created one public and one private. Now I want public subnet to be able to communicate with the internet. Now to do that, I'm going to come back to the route table. And the route that I just created that is connected with my public network, I'm going to add another route to it. Now the IP address of if you want basically the IP address of internet is 000. This actually means that we allow everything, traffic from everywhere. This essentially means internet. So I'm saying that. Wait, let me just. So in the target, I'm gonna. Oh, okay. Sorry, I forgot one thing. So whenever you create your internet gateway, you have to connect it to a VPC. I forgot to do that. So attach to VPC. Okay. Sorry about that. Add route. So I told you that to connect to internet, you have to write 0.0.0/0. This means that allow or allow traffic from anywhere or send traffic to anywhere. And then in the target, you will actually enter your internet gateway. So this actually means that redirect all the traffic to or from internet through this internet gateway. This is what this route is saying. And if I save this now means that my subnet has access to internet. It is as easy as this. Now my public subnet has access to the internet, but my private one doesn't have it because I did not add any such route in my private subnet. Okay. Now, sometimes you might also want to access internet from your private subnet. Now, but you don't want internet to access your private subnet. So basically, how this would work is that you would create an sorry, a NAT gateway. So what a NAT gateway does is that whenever your private subnet needs to communicate with the internet, it would send a request from the NAT gateway to the through the NAT gateway to the internet, and the internet can only send the response of that request back to the subnet and nothing else. Other than that, the internet cannot access your private subnet. So if you want to access internet from your private subnet for some reason, you can do it through NAT gateway, which is, you can say, in a way, one-way communication. So only your subnet can initiate the communication with internet. Although the internet can actually send you the response of that request, but it cannot send you anything. It cannot like access your subnet whenever it wants to. It can only send the response of the request that you send to the internet through your NAT gateway. Now I'm not going to show you how to make that. Uh, it's quite easy. You can Google it, but I'm just taking you through the theory. Now, two other important things, because we don't have much time left. Two other important things are security groups. You can use security groups to, it works like a firewall that actually monitors your inbound and outbound traffic. And then you also have ACLs, which again is a kind of firewall. Now the difference between ACL and security groups is that security group sits between subnet and your instance. So it is basically a firewall for each of your instance, like a firewall for your instance sits between your subnet and security group. So it only filters out the requests after they have entered the subnet. This is where you use the security group, and we will actually use it in our Neptune code, in our CDK construct. But the ACL, again, it works very similarly to security group. There are differences, but I don't have time to discuss them. But ACL sits between the routing table and the subnet. So you can say it works on a higher level. This works on the instance level. This works on the higher level, on the subnet level. So this is the difference between these two. So you can actually create a very good security control using these two, security group and network ACL. So I think these were the important concepts regarding VPC that you needed to know. Okay, now let's move on to Neptune. Now your Neptune can only be initialized inside the subnet that I showed you. Let me go to now. I have already deployed the code from our code. But before actually going through that, I would actually like to show you how you can create a database from the console, because there are a lot of parameters over here in the console that you need to know. So what you need to do is create a database. So first of all, you have to choose the version. So you can also choose from the previous version. So I think the one is basically the major upgrade. Then I don't know. Yeah, this means the second decimal number means I don't know, second version, a smaller version. I don't know, something like that. So basically, I have selected the latest version, and then uh, you have the name of your cluster or database, and then you choose the template whether you want to do it for production or development and testing. The difference is that if you choose production, the instance that you create, you have a broader range of instances that you can create from. And what is an instance? So basically, it actually depends on your requirements. So you can see, choose a database instance class that meets your processing power and memory requirements. So basically, if you have a huge database or a huge graph, then you would use the largest one. So you can see it has a lot of memory, 768 GB. But it would obviously be costly. It also has 96 CPUs. So with larger instances, you get more processing power, more memory, more RAM. With smaller ones, you get they're obviously they're cheap, but you get less memory and less processing power. And in development and testing, you can actually use this one. I think this is the cheapest one. They have actually made this just for development and testing. It is a very small instance that only has 2 CPUs and 4 GB RAM. But I think it's like it might be the cheapest one, or I think it should be free. I'm not sure. Anyways, okay, moving on. Now you can also, I told you before that you can actually create read replica in different zone. It's up to you to increase availability. And then connectivity, you have to connect your Neptune with a VPC. So you can choose a VPC that you want to connect it with. And in the additional connectivity configuration, you choose the subnet group. You can either create a new subnet group from over here, or you can choose an existing one. And this is the port for your Neptune, like the IP address, or you can say the port inside your VPC, inside your subnet, through which your Neptune would be accessible. And then you also have some additional configuration. There's just some authentication options over here, backup options, encryption options. Not really important for now. Logs option, you can actually log uh, you can log the operations of your database. Then you have maintenance options, that when do you want to maintain, like do you want to enable auto minor version upgrade or not. And there's some deletion protection. These are not really important. I've discussed the important ones. So I'm going to cancel this now, because we're going to deploy it from the code. Now this is the code. Sorry, this is the code. I've already deployed it because it takes a lot of time for Neptune to get deployed. You can see a few errors over here that are because of the problems in my dependencies, but this code works. I've just deployed it. So are you guys saying something?
No. Yeah.
Okay.
I
Okay.
think Sir might be trying to say something, but we can't hear him.
Oh, okay. Okay, I'm just gonna move on. Sir was actually trying to say something, but we cannot hear him properly because of the connection issue. So I'm just gonna move on because we don't have much time left. So you can see in this code, we have first created a VPC, and I told you that VPC is you can only create Neptune inside a VPC, and inside this VPC we have also created a subnet, and you can see in the subnet we have passed the subnet mask. The value of subnet mask that we have passed is 24, and also say the way that it will create a range of IP addresses, a range of 256 private IP addresses, and the name of the subnet is ingress. Okay, the type is isolated. Now, up till now, I have discussed two types. Number one is the public type, which can openly access internet. Second is the private type that can access to the internet through net gateway, which is, you can say, a restricted access. If you create an isolated subnet, this means that you don't want to access you don't want to have access to the internet at all. So in an isolated subnet, you would not be accessing internet at all. And this is the kind of subnet that we have created. Now CDK actually have this, I don't know, it actually automatically creates a isolated subnet for you. I'm not sure what kind of configuration does it set for it, but we'll see it. So, and then we have created a security group. So this is the thing that I was talking about here, that sits right above your instance. So it will sit right above our Neptune instance. And in our security group, so in a security group, you can define two kinds of things: rules for the outbound traffic and rules for the inbound traffic. Uh, rules for the traffic that is coming inside your instance, and rules for the traffic that is going outside your instance to the subnet. So you can see over here, we are saying, first of all, we have attached it with our VPC, and then we are saying allow all outbound true.
Varis,
Yes.
can you please zoom in?
Oh, sorry. Yeah, sorry about that. Up till now, I've only discussed this. We have just created a VPC. Now we are creating a security group, and in this security group, we have linked this security group with our VPC, and then CDK actually gives us a parameter to allow all the outbound outbound traffic. So by just making it true, we are saying that we are not putting any restriction on the outbound traffic. Like anything that goes outside this instance in the subnet um, shouldn't be blocked. Uh, The security group should let it go. And then this is the description, not important. Security group name, this is also not important. And then we have added some tags to our security group. Again, this is not important um, in terms of functionality. In terms of management, yes, it is important. And then what we have done is we are saying we want to add an inbound rule. So ingress means inbound. And we are saying that we want to add a rule to this port. And what is this port? As I've already deployed this code, let me show you. This is the cluster that I've deployed. So if I go into the settings, it shows me the port of this cluster. So the basically 8182 is the port of our Neptune inside the VPC. And in the inbound rule over here, we are saying that anything that is coming inside our Neptune through this security group should be allowed to should be allowed as long as it is going to this particular port, or in other words, as long as it is going to our Neptune database. So anything that is coming from over here from the subnet into the instance should be allowed as long as it is going to the 8182 port. That is our Neptune. So this is all that means. So uh, we added no restriction on the outbound traffic, but in the inbound traffic, we are saying it should only be allowed if it is going to the 8182 port. That is our Neptune cluster or Neptune database. And then we have created our subnet. Wait a minute. Yeah, okay. So here we're actually attaching the subnet that we created over here with our Neptune. Now Neptune has to go inside a subnet, right? Now because we're using a CFN um, L1 construct, you may see a lot of different parameters. You may see the longest coder because L2 constructs are not yet available for Neptune. So we are saying using L1 construct to actually attach the subnet that we made over here with our Neptune. So you can see in the subnet IDs, we are saying the subnets of this VPC, select subnets with subnet, this subnet that we created up here, and dot ID, subnet ID. So this actually is asking for the IDs. So we are passing the IDs of this subnet that it needs to go in. And this is the subnet group name, not important. And then we are creating a cluster. So in CDK, because this is L1 construct, we have to write separate functions for creating a cluster and an instance. But I believe when an L2 construct would come, we can do both of these in just one function. So in the cluster, you actually define the subnet group name. Okay, so in the cluster, basically you are attaching your security group with your subnet for the Neptune. And then in the instance, you're actually telling that which instance do I want to show? Do I want to use? So I showed you that we can use different kinds of instances depending on our needs. So here we're using the medium instance, which is not too expensive, but not very powerful. And then availability zones. I'm not sure what this means. Yeah, they are, because this is a L1 construct, there are so many parameters. I'm not exactly sure what does each of them mean. But you can actually go through them in your own time. But it is quite straightforward. And because we're using L1 construct, you also have to add this add depends on at certain places where you actually want this to create before this. So by add depend on, we're saying that we want this to create first because this is actually dependent on this thing. So this has to be created first before this. But you would not see this function in an L2 construct. Okay, this is important. Now up till now we have just created a VPC, a subnet, a security group, and then we have put our Neptune inside that subnet. And now we are creating a Lambda function. And the code comes from this folder. I'll show you in a bit what it is. and the handler is index. Now we are attaching our we are putting our lambda function inside VPC. So you can see in VPC we have referenced our VPC. In security groups we have referenced our security group, and this is we're just passing the Neptune endpoint in our environment that we would need to connect with our Neptune, and then we are also writing this VPC subnets in which this lambda function would be, and then we have created an API gateway that we have attached with our lambda function. Now, if you just look at this code, you would assume that this lambda function is sitting inside your VPC, but that is not the case. That is not entirely the case. So when you actually say that I'm putting my lambda function inside my VPC, it doesn't entirely go inside your VPC. Let me show you what happens. Okay. Okay. Now, when you say that I'm putting my lambda function inside my VPC, it doesn't go inside your VPC, not fully. So this actually means that the invocation right of your lambda function stays inside the VPC that is for your AWS lambda service. So your AWS lambda service works inside in its own VPC. Most of you might not know that the lambda service has its own VPC from which it operates. So the invocation rights of your lambda function stays with the VPC of lambda service. So even if you put your lambda function inside your custom VPC and it doesn't even have access to the internet, it can still be invoked from anywhere from the internet. Why? Because the invocation rights come from the VPC that is VPC of the lambda service. So even if I cut the internet connection from a custom VPC and I'm saying over here that I'm putting my lambda inside my VPC, I can still invoke it from the console or from this API gateway that I made over here. Although this API gateway is not in my VPC, but I can still invoke this lambda function from this API gateway. So then the question is that, like, what is the use of putting lambda function inside my custom VPC if I can invoke it from anywhere? Well, the answer to that is that the invocation right stays with the lambda VPC, but what runs inside your handler? Let me repeat this: the invocation rights stay with the lambda service VPC, but what runs inside your handler is bound to the rules of your VPC. So if my VPC does not have access to the internet, although my lambda would be invoked from an API gateway or from the console, it might not be able to access the internet if my VPC does not allow that. So this is what is actually meant by putting lambda function inside your custom VPC. So invocation rights stay with the lambda service VPC, but the accessibility inside the handler gets bound to the rules of your custom VPC. This is what I have understood. There was quite a bit of confusion regarding this, but this is what I have understood. And this sounds, this looks okay up till now as far as I have tested. But let me know if I'm wrong, maybe in the comments. Okay, now this is the CDK stack. So we have created a lambda function. We have created a VPC. In the VPC we have a subnet. In the subnet we have our Neptune, and then we're also saying that we want our lambda function inside of a VPC, which I just told you what do I mean by that. So the handler of this lambda function would be able to access everything inside my personal VPC, but not internet, because I have not given access to the internet to this VPC. And then I have created an API gateway that would be connected to my lambda function. Now, although this API gateway has nothing to do with my VPC, it would still be able to invoke my lambda function from the internet. And the handler of my lambda function would only be able to access the information that is inside my VPC. And what is inside my VPC? My Neptune. So my lambda function would be able to access Neptune because it is now inside my VPC. But my lambda function would not be able to access the internet from inside the handler. Now let's have a look inside let's have a look at the handler of this lambda function. And in that handler, we are actually trying to create a connection with our Neptune and run queries in it. Now there's a lot of code over here. It may seem confusing to you. So I can start from over here. So what I've done is I'm getting this environment variable from my environment variable from the stack, and I have actually initialized two variables. One is con that has type of driver.driver remote connection. And where is this coming from? This is coming from the Gremlin library that we installed. Now you need to import this library to initialize the connection with your Neptune database. So I've just initialized the variable over here, and then I've also initialized a G variable over here that is of type G process graph traversal source. And then I've used a condition over here. I'm saying that if this variable is false, or in other words, if there is no connection, so this variable would hold the connection between the Neptune and my lambda function. So in other words, if there is no connection, then run this function and save the return value of this function inside this variable. And what is this function? This function is made over here. So this function in the first line is saying that get connection details, which again is another function. And this function does nothing. It just returns the URL that is needed to connect with your Neptune. So this URL is provided by Neptune. So we need to connect to this endpoint to connect to our Neptune database. So this function is just returning this URL, and then we're getting over here, and some headers as well. Right now we're not returning anything. So it is returning a URL and headers, and we need this URL to connect to our Neptune database. And then we're creating a new instance of the driver remote connection, and in that instance we are passing our URL that we got from here, from this function, and some other properties. Now I'm not exactly sure why do we need to send them, but this is how you actually create a connection with your Neptune. And then okay, this is it. So this thing is being returned from this function, and it is being saved in this variable, and this actually creates the connection with your Neptune, the connection of your lambda function with your Neptune. And in the second line, we are saying in the variable g that we initialize over here, we want to run this function and return the return value of this function should be saved inside this variable. And this function is taking this variable as an argument in the argument. So what is this function? This function returns gprocess.traversal.widRemote and takes in connection. Obviously, it's not very straightforward. It's hard to understand what's happening, but you would not have to change this code at all, because this is just, you would always keep this code because this is the standard code to create a connection with your Neptune. You would never change it or delete it. You would leave it as it is. So basically what we did over here was that we created a connection with our Neptune database, and over here we initialized a traversal source. Now what is a traversal source? You need a traversal source in your graph database to be able to traverse or write queries in your database. You can assume it to be a kind of initialization of the database, but you actually need this variable to be able to write queries or traverse in your database. And this comes from Gremlin. The Gremlin library returns us this. And then in the return value of this function, we are running this async.retry function. What this does is that it first tries to run this function. And what is this function? Let's have a look at it. So this function is made over here. It calls another function, this one, and this function is returning a query. So this is how your query looks like in Gremlin. This is basically a query. It is a meaningless query, doesn't do anything, but this is how queries look like. So this function is returning a query, so we are saving query over here, and we're just returning this object. So we are saying basically we're trying to run this function in this async.retry function. So, and if this function fails, then it's going to come over here. So it's first going to see that if the error was something like this, if the error was something like that WebSocket is not open, then try to create the connection again, like run this thing again. If the error was something like this, then don't do anything but just warn the user that retrying query because of current modification exception. And if the error was something like this, then just just warn the user about this thing. And after each error, and for each error, it's going to try for 5 times with an interval of 1000 milliseconds. Now this may be a bit confusing for some of you to understand because of the way it is written, but let me repeat this. So it's going to try and run this function. If it fails, it's going to run either one of these conditions, and it's going to try running this function again 5 times, maximum of 5 times, with an interval of 1000 milliseconds. That is 1 second. And what does this function do? This function actually runs a query inside our Neptune database. And you can see this G over here is the same thing that we initialize over here, this traversal source. And you need this to be able to run and create queries. So essentially, you would not change anything in this code if you want to run Neptune. Nothing in the stack, nothing in the Lambda function. You would only change this line over here. You can add your own queries, and so you don't have to change anything else, because everything else is just initializing the Neptune for you and nothing else. And I have already deployed it. So this is my database. You can see this is my wait. So this is my primary database instance. This one. Oh wait, this one. This is the one, right? Homa, which one is the primary database instance? Do you know?
Actually, you have not made any replicas, so this is your only writer, and
Okay.
this is your only reader.
Okay. So this is our primary database instance. If you want to create replicas, you can. I'm not sure how do you create it.
Are you there, Varis?
Maybe modify. Hello.
Yeah,
I think I got
right.
disconnected. Yeah.
Yeah.
Okay. Yeah. I was just trying to find out how to create a replica. Yeah. Yep. I think my internet is quite slow. I might not be able to do it. But here you go. You actually have to select this cluster and then add reader. So this will create a replica for you, and you can have up to 15 replicas. Now, one way of writing queries is through Lambda functions that I just showed you. You can change your write your query over here and then deploy the stack, and it should run in your Neptune. The other way, the faster way of actually checking queries or mutations in your Neptune, you can create a notebook. So let's create a notebook. You can also select the instance type of a notebook. For now, I'm going to leave it medium. Test notebook. You can also select a role for your own notebook in case you want to access some other resources in your account through the notebook. and that's it. So this notebook is basically a part of another service of AWS called AWS SageMaker. But in this case, in the Neptune, we can actually create a notebook to actually run Gremlin inside it. Although it's a Python notebook, it's a Jupyter notebook that is usually used for Python. But they have also given us a custom plugin that allows us to use Gremlin in the notebook, and it's a very easy and fast way to run your queries and test it with Neptune. There are also some other fast ways to run queries and test them that we will see in the next lecture. So one way is to actually write it over here and then deploy the code, run the Lambda function. The other way is to quickly run your queries and to quickly check what's inside your graph and what's inside your database. You can use a notebook. Now it may take a few minutes to initialize the notebook. Now this obviously comes with a cost. I think this is not free. Neither the notebook nor the Neptune database is free. It charges you per hour. I'm not sure how does it charge you, but make sure that you either stop your instance or delete it, and make sure to delete your notebook as well when you're done with your project or playing around with it. I'm just waiting for this notebook to get initialized so that I can show you some Gremlin queries. So you can see it's written over here: quickly and easily query your Neptune databases with Jupyter Notebooks, fully managed interactive development environment with live code and narrative text. Notebooks are hosted and built through SageMaker Notebook Service. So although this notebook is not a part of Neptune, they have actually integrated two different services together, SageMaker and Neptune, so that you can run Gremlin queries easily on the console itself. And inside this notebook, they have also given us very nice tutorials, very comprehensive tutorials for Gremlin. But this is not the free way of using it. To be able to run all, because neither the Neptune nor the notebook is free. To be able to use Gremlin, and if you're just trying to learn Gremlin, the to be able to practice it freely or without any cost, you have to download the what do you call it, Tinkerpop console. Am I right, Homo?
Yeah, Tinkerpop server and Tinkerpop console.
Yeah. So if you don't want to spend any money while you're learning Gremlin, then you can download that, and we will see that in the next lecture. But let me just warn you again that this can actually cost you money. So be mindful of that. Okay, our notebook is ready. So I'm going to click open notebook. So it's going to open a Jupyter notebook. I'm pretty sure everyone has seen a Jupyter notebook. As you can see, it says SageMaker. It's taking us to another service. Now we have another step in this. We have another step too. I've just discussed the Neptune Lambda step. There's also a step to run your Neptune inside an EC2 that is running inside a VPC. Now, I don't think we have much time to discuss that, but the code is pretty much similar to this one. And then there are some instructions after the code that you need to follow to be able to properly run this example. So I think you can do it in your own time because the rest of the code is pretty much the same. We've just created an EC2 over here and some extra roles.
Actually, may I add something? We have created EC2 not to put our Neptune inside that, but to access Neptune within that EC2.
Okay, so let me thank you for correcting me. So right now we're using Lambda to access the Neptune, and in the second example we're going to use EC2 to access the Neptune or to write queries or write mutations.
Right.
Okay. So you can see they have actually given us sample application as well. They have given a very comprehensive tutorial for us. So I'm just gonna click on getting started, and you can see they've also given you tutorials for RDF, the other kind of graph that I was talking about in the beginning, and they've also given you a tutorial for the Gremlin. So I'm just gonna open one example. Now you can also, if you don't want to open these examples, you can create your new notebook and start writing over there. But I just want to show you. So you can see this is the if you really want to learn Gremlin properly with a proper tutorial, you can actually go through these tutorials. Now what I can do is I can show you. Now if you want to use, now this is because this is usually used for Python. If you want to use Gremlin, you have to first write this line, percentage Gremlin, and then you would be able to use Gremlin. Now let me just show you a few basic queries that you can write in Gremlin. Now let me just go back to this page. Now, I told you we have two kind of things. We have vertices and we have edges. So let's first create a vertex. Right now our graph is empty. We don't have anything because we just created a graph. Now let's create a vertex. So to create a vertex, you write what do you write to create a vertex? Add.
G.add.
Oh, sorry. Add. So this is the traversal source that I was talking about. The notebook initializes it for you. And you write label in here, right? You write it like this. Mama, can you please help me? I've actually forgotten.
Yeah,
Okay.
you will
I
add
can
the
actually
level.
follow this example. It's okay.
You will add level.
Basically, I've not used Gremlin much, and I don't have a very good memory. So
Even if you use it much, you will have to go through it again.
yeah. So basically, if you want to, there's also a cheat sheet for Gremlin. Gremlin cheat sheet. So if you keep forgetting the commands, you can go through this cheat sheet. So I was trying to add a variable, so you can see they've given you a command to add the vertex. So let's just quickly make this thing over here. So I'm going to create one. I'm going to add one add. So first, I'm going to create this vertex, Bob. And so this the type is user. So this is the label. Whatever you put over here is the label. And property. What is the property of?
Whatever property you want to do.
So
First name
here
and
we
last
have
name.
two properties: first name and last name. So I'm gonna write first name. This is the key of the property, and now I'm gonna write the value of the
Value.
property. That is Bob. Let's just take your first name for now, and then I can just run this, and it's gonna create a vertex for me.
I'm not sure.
You can see.
The notebook asked for dot next. Okay, it's done without next.
Oh yeah. So yeah, that's a very good point. So if you're writing your queries inside JavaScript, you would have to add these terminal steps. Now we will discuss more about the terminal steps in the next class, but you don't need to add terminal steps in the notebook. But when you're writing your code in JavaScript, you would have to write your terminal steps, and it would mostly be next or to list or to iterate. But there are many different kinds of terminal steps that you can add. And what are terminal steps we are going to see in the next class. We don't have much time left. I'm just quickly trying to show you some queries. Now I've made my vertex. Now what if I want to get it? Now label. What was my label that I want to get? It was user. What this query would do is it will go to my graph, and it will fetch all the vertices with this label. Right now I only have one user label, so it's only gonna show me one entry, just you can see. But you can see this is not a readable form. This is showing me the ID of the vertex. To get the first name of the vertex, what I have to do is I can add values. This shows me the properties of the vertex. And you can write value map to also get the ID of the vertex. So you can also get the key. Then you can also get the key of the properties with the values. Now, if you also want to get the ID of the vertex, you can write true. I'm just showing you how to play around with the queries. obviously, this is not a full tutorial of Gremlin. We will see that in the next class. But this is how you basically play with your graph, and this is how you would be writing queries. And notebook you can use it very easily to quickly check that what is inside your graph, and if you want to test any query, you can easily do it over here instead of doing it in your Lambda function. So I think that's it for today, because yeah, we have gone. What time is it? Yeah, okay. I don't think we have much time left, so that is it for today. We're going to have a look at the Gremlin and Tinker Pop in the next class. So, do we have Sarzia in the?
Sir, are you with us?
Yeah, yeah, yeah. Okay, we cannot hear. Sir, we cannot hear you. Okay, I think Sarzia's net is not working today. So this is it for today. Do you want to add anything, Homa?
Thank, thanks a lot, Varis. That was brilliant class. Oh, it was
Yeah.
best of the best.
Okay, thank you so much. Okay, see you guys in the next class. Bye bye. I'm sorry,
Class.
I cannot hear Sarzia, so sorry, sir.
Me
Bye
too.
bye.